So the ozone layer. Ozone layer. Okay, first you need to know what the chemical formula of ozone is. So the chemical formula of ozone is O3. You need to know whereabouts we find the ozone layer. And the ozone layer is in a part of the atmosphere called the stratosphere. A part of the atmosphere called the stratosphere. And the ozone layer prevents harmful UV light. So the ozone layer prevents harmful UV light, UV rays from reaching the atmosphere, from reaching the Earth's atmosphere. And we're bothered about this because it can cause skin cancer. Prevents harmful UV light from reaching the Earth's atmosphere. It can cause, if it does reach the Earth's atmosphere, it can cause skin cancer. Okay, so ozone has a formula O3. It's found in the part of the atmosphere called the stratosphere, and the purpose of the ozone layer, the purpose of it is that it prevents harmful UV light from reaching the Earth's atmosphere, and we are concerned about this because if UV light comes through to the Earth's atmosphere, it can cause skin cancer. Okay, so we've got a picture here. Take a look at this picture taken from an OCR textbook. Okay, so it shows here that you've got the atmosphere, and the atmosphere is very simply split up into two regions, the troposphere and the stratosphere. So the stratosphere is the upper atmosphere, and the protective ozone layer is there. Okay, so the protective ozone layer there prevents the harmful UV radiation coming in and reaching the Earth. And then, but there's ozone up here. But if you get low level ozone in the troposphere, which is caused as a pollutant from lorries and cars and trucks, too much here, cars, trucks, power plants and factories, all emits air pollution that forms ground level ozone, which is a primary component of smog, and that can cause respiratory problems. Okay, so that can cause respiratory problems, breathing problems. So ozone up in the stratosphere is good. So ozone up here is called the good ozone. But if you have ozone, a low level ozone, we call that the bad ozone, because that causes breathing problems. Okay. Right, we need to know a little bit more detail. So here's another picture just taken from the OCR textbook. Okay, from the sun, we actually get UV light coming from the sun. And in chemistry, we split it up into three types of UV light: UVA, UVB, and UVC. So we're going to do UVA first. So I'm going to draw a little arrow. So UVA is the lowest energy UV light. Okay, it's low energy. You do not need to remember the number, the wavelength, but it is 320 to 400 nanometers. It's a long wavelength, and it is low energy. Of the three, it's the low energy one. Okay, now we're not very concerned about this. So the ozone layer here, the ozone layer in the stratosphere, absorbs 5%. So 5% of the UVA is absorbed, so therefore 95% hits the Earth and comes through to the Earth. But we're not worried about it because it is low energy and it does not cause any harm. Okay, it does not cause any harm because it is low energy. So we're not worried that the majority of it gets through to the Earth. Okay, so that's UVA, the low energy UV light. And then if we go to the other side, which is a UVC, therefore if UVA is a low energy, UVC, you can probably work out, therefore is the high energy, which is the short wavelength. And again, you don't need to remember the specific numbers. I've got 200 to 280 nanometers here. It's short wavelength, and it's high energy. Okay, but again, we're not very concerned about this because you can see here what it says, that 100% of UVC is absorbed by the stratosphere. So none of it comes through to Earth. So we're not concerned about it. Okay, it is entirely screened by the ozone layer. None of it comes through to Earth. Okay, so if that's the high energy one and that's the low energy one, the one we are most concerned about is the one in the middle, UVB. And you can see here it says UVB, so this is the middle energy one. Okay, in between the two, 95% is absorbed by the ozone layer. Just 5% comes through to the Earth. But this is the one that can cause skin cancer. Okay, so prolonged exposure to this one, prolonged exposure causes skin cancer. And if there are holes, if the ozone layer is thin in places and there's holes, then more UVB is going to be coming through and hitting the Earth and can cause more skin cancer. Okay, let's put that written at the bottom. If the ozone layer decreases, more UVB radiation will reach the surface. So that is the one that we're most concerned about. Okay, so what else you need to know about this, about the ozone layer for chemistry, for OCR, A-level chemistry? So you need to know how the ozone is made in the stratosphere. Okay, so how is ozone made? So I'm going to put the formation of ozone. How is it made? Formation of ozone. Okay, so first the oxygen molecules in the atmosphere, they absorb the high energy, the UVC, the high energy. They absorb radiation, which is less than, you don't need to remember specific, 240 nanometers. You just need to know that basically this is the high energy UVC. Okay, so the oxygen molecules absorb this and it breaks the bond between the oxygen molecule. Remember, the oxygen molecule is a double bond like that. Okay, so it's a very strong bond, so it needs high energy to break it. And when that bond is broken, you're going to have two oxygen atoms. Okay, so that's the first step. And then the second step is that another oxygen molecule and an oxygen atom are going to join together to make what? To make the ozone. This is how ozone is made in the atmosphere. Also, it releases heat. Heat is released, which is just absorbed by the air molecules in the stratosphere. So that's just absorbed. The heat is absorbed by the air molecules in the stratosphere. Air molecules in the stratosphere. So what's basically happening when we are converting, when we are making the stratosphere, in the stratosphere, when we are making ozone, we're converting the high energy UV light into heat, and that's being absorbed by the air molecules in the stratosphere. Okay, so that's the first step, oxygen, and this is why UVC does not go through the ozone layer, because UVC is being used up to break down the oxygen, molecules into oxygen atoms, which then combine with another oxygen molecule to make ozone. Okay, now at the same time in the stratosphere, as the ozone is being formed, the ozone is being broken down as well. So we're going to say breaking down of ozone. Breaking down of ozone. Okay, so ozone at the same time is being broken down. Okay, so ozone, and there's this weaker bond in ozone, so it can absorb the radiation, the lower energy radiation, which is 310, below 310 nanometers, which is basically the UVB. The UVB, which is the medium radiation, and then that can break down the ozone back into an oxygen molecule and an oxygen atom. Okay, so that is why, again, that a lot of the UVB does not get through the ozone layer. 95% does not get through because it's actually being used up. It's being used up to break down the ozone. Okay, so if we look at what's happening here, we've actually got in the stratosphere that the ozone molecules are being made. The ozone molecules are being made, but at the same time the ozone molecules are being broken up. So there is a natural steady state equilibrium. A natural steady state equilibrium. Natural steady state equilibrium, where the ozone molecules in the stratosphere are being made and the ozone molecules are being broken up. And this just happens, the rate of the forward reaction equals the rate of the reverse reaction. And this is just naturally occurring in the ozone layer. And that what happens is then humans put pollutants up into the atmosphere, and then this messes about, this damages this natural steady state equilibrium, and it is not in equilibrium anymore. Okay, now which kind of pollutants can damage the ozone layer and mess about with this natural steady state equilibrium? So the major pollutants, there's several pollutants, but the major pollutants that can damage the ozone layer and break up the natural equilibrium are CFCs. And CFC stands for chloro, so that's the C, fluoro, that's the F, chlorofluorocarbons, and that's the other C, chlorofluorocarbons. Okay, so chlorofluorocarbons are used to be used as aerosol propellants, so in cans, spray cans, like deodorants, used to be used in aerosol propellants. They used to be used as the coolants for refrigerators. Okay, fridge coolants. They used to be the chemicals, and they used to be used in these items because chlorofluorocarbons are non-toxic. They are non-flammable. These chemicals are. They're non-flammable. That they don't smell. They're very stable. They are unreactive. Very stable, unreactive. They don't smell, and they thought they were the ideal chemical to be used as a propellant in an aerosol or as a refrigerant. But the problem is, because they are so very stable and so very unreactive. Okay, now there's many CFCs, so if you take like the simplest CFC, that is like an example of the simplest CFC, but there are many different types of CFCs, carbon, fluorine and chlorine. They're very unstable, very stable, and very unreactive. So what happens is they do not break down in the lower atmosphere, okay? They do not break down in the lower atmosphere. They stay around in the atmosphere for decades. So these molecules stay in the atmosphere for decades. For decades. So you spray it, you spray one of these aerosols, and for tens of years, that gas is still going to be in the atmosphere. Because they're very stable and unreactive, the only way they can be broken down is by the high energy UV radiation that is in the stratosphere. So they only break down once they're in the stratosphere, and it can take decades for the gas to reach the stratosphere. Okay, and then what happens when they reach the atmosphere, when they reach the stratosphere? So you need to know what happens. So first, if we take the simplest, now you could be given an exam question. You could be given any chlorofluorocarbon, but I'm just taking a very the simplest example here. And the high energy UVC breaks the bonds because they're very strong bonds. CF is a very strong bond, and CCl is a very strong bond as well. Okay, so the first step is that you could break off a chlorine radical. Okay, so you are left with, remember, a radical is an unpaired electron, and that first step is called initiation. Initiation. Okay, so this happens in the stratosphere. And then the chlorine radical will react with an ozone molecule and will generate another radical and oxygen molecule. And then that radical, ClO radical, will react with an oxygen atom and to regenerate the Cl radical. And can you see what we've got there? We've got oxygen molecule. These two steps together are called propagation steps. Propagation steps in the mechanism. Okay, so can you see as well that this Cl radical is now going to be able to go and break down another ozone molecule. If you add these two propagation steps together, just the propagation steps, okay, we can see that the Cl cancels out left and right, the ClO cancels out left and right, and you're left with O3 plus O goes to 2O2. So that's the overall equation for the depletion of the ozone layer. Overall equation for the depletion, the breaking down of the ozone layer. So one ozone molecule is being broken down into two oxygen molecules. Okay, this is an example of homogeneous catalysis. Homogeneous catalysis. Because the catalyst is the chlorine radical. Okay, and here you can see the chlorine radical that is generated can just go and break down another ozone molecule. Okay, and it is said, it's been calculated that one CFC molecule, one chlorofluorocarbon molecule, can actually break down 100,000 ozone molecules, can destroy 100,000 ozone molecules, which is a really scary thought. So that one CFC molecule can actually destroy 100,000 molecules. Okay, but this is an equilibrium. It's an equilibrium. It's a natural equilibrium where ozone is made, and where ozone is formed down. So if we stop polluting, if we stop putting these CFCs into the atmosphere, then the equilibrium will come back. The natural equilibrium will come back, and it will start to repair. It will just take many years to do that. Okay, so CFCs are the main chemicals that deplete the ozone layer. Okay, there's another chemical as well as CFCs. The other major chemical that you need to know about comes from the CFCs, but also the other one is from lightning. There's nothing we can do about that. And aeroplane engines. So the other pollutant that depletes the ozone layer comes from lightning and aeroplane engines, and that is the NO radical. So lightning is the nitrogen and oxygen in the air, and causes the NO radical. And then it's exactly the same mechanism how it depletes the ozone layer. So you get NO and the ozone molecule, and then you get NO2 radical plus oxygen molecule, then the NO2 radical plus an O atom gives you back your catalyst, your NO radical, and oxygen. And so the overall equation is exactly the same. If you cancel out the left and the right because they're identical, you've got O3 plus O going to 2. So this is the equation for the depletion of the ozone layer.